In this video, we're going to be discussing programmable logic controllers, which are more commonly just referred to as PLCs. Now we're going to begin with a general overview of PLC function and operation so that we can begin to understand how a PLC would perform in a given function. Next, we're going to discuss the pitch system of a wind turbine, and we're going to look at some of the specific requirements of that particular system. And then finally, we're going to look at how the pitch system employs PLCs in order to perform its various different functions. So the first thing to consider is what programmable logic controllers actually are. And the simplest way to understand the role of a PLC is to break its name down into its three constituent parts. So first of all, we have programmable. Now a PLC is basically just a microcomputer, and programs are written according to specific requirements and functions. So a PLC programmer will be given a specification or a set of requirements, and they will write a PLC program accordingly. And there's various different types of software that can be used to program different PLCs. The second part of the name is logic. Now the types of programs that PLCs use are logic-based programs, and in fact the majority use something called ladder logic. So the programs themselves are based on logic functions, but we also have various different sequencing and timing functions as well. We're going to spend a bit more time looking at some of these logic functions later in this tutorial. Now the final word in the name PLC is controllers. And the controller is the part of the PLC that actually runs the programs. So as it states there, the controller receives inputs and it controls output devices according to custom programs. And we'll look at some of the different types of inputs and outputs next. But in principle, the controller receives inputs and then it controls outputs. And it will be the PLC program that determines that relationship. So on this diagram, we see some examples of different inputs and outputs. So on the left-hand side, we have our inputs, things such as sensors and switches, and they're used to detect information or detect conditions within a system. Those inputs then feed into the PLC, which will be controlled by the logic-based program, and the PLC will execute programs based on the inputs. So if the inputs change, the program might be executed in a different way. And finally, we have our outputs, things like motors and indicators as an example. So the outputs are determined by the inputs and the programs that are executed within the PLC itself. So on this diagram, we see a bit more of a breakdown as to what makes up the PLC. Now, first of all, each of our sections requires a power supply. So on the left-hand side, we have the inputs with their power supply or their power source. And on the right-hand side, we have our outputs also with its power source. In the centre, we have the PLC. And the PLC is made up of a CPU, which is basically the processor, the thing that runs the program. And we have the memory, which is where the program's stored. So the PLC programmer will write the program. That program will be stored in the memory, and the CPU will access that memory in order to execute the program. Now, another important factor of the PLC unit is that it can be integrated with different communication systems. One of the more common communication systems would be SCADA, which stands for Supervisory Control and Data Acquisition. All that means is the SCADA system collects and represents data. Another name for these types of systems is HMI, and HMI stands for Human Machine Interface. If you like, it's a way for an operator or technician to see visually what's happening within the PLC, or what's happening in terms of inputs and outputs. And we'll look at some specific examples of this in relation to a wind turbine later in the video. But next, let's take a look at some different logic functions so that we can start to understand what's actually happening inside our PLC controller. So we're going to start with some very basic functions, and what we have on the left-hand side is a logic function called an OR function. At the top, we have a representation using ladder logic. In the bottom left, we have something called a truth table, and in the right we have the symbol that represents that function. If we start at the top with our ladder logic diagram, we can see that input A is open and input B is open. That shows their normal positions, so these two switches are normally open. Therefore, if A is not activated and B is not activated, then a signal can't travel from the left-hand rail to the right-hand rail. There's nowhere for that signal to pass. Here we just see an indicator lamp that will light when either A or B is activated. And the reason it will light when A or B is activated is because closing A will allow a signal to pass here. Closing B will allow a signal to pass here. Now we also notice that if both are closed, then the lamp will still light. So the way this information is represented on the truth table, in our normal condition, A and B are not activated. And if A and B are not activated, then we don't have an output. However, if just B is activated, as we mentioned, we'll get an output. If just A is activated, we get an output. And if A and B are activated, we still get an output. Although this is called an OR function, this will also provide an output if A and B are activated. If we look at the diagram on the right hand side, we see a different configuration. Once again, A and B are normally open. We see our left hand rail of our ladder and we see our right hand rail, and signals are going to want to travel from the left rail to the right rail. But at the moment, because A and B are normally open, in their normal positions, the signal can't pass. Now this function here is called an AND function, and the reason it's called an AND function is because for a signal to get from our left hand rail to our right hand rail, both A and B need to be activated. If we activate A, but B is not activated, the signal can't pass, and vice versa, if we activate B, but A isn't activated, the signal can't pass. So the signal will only pass when A and B are activated, and we see that represented on our truth table. The only situation where we get an output is when A and B are both activated. So the next function that we're going to look at is called a NOT function, and that's the function on the left hand side here. Now with a NOT function, we're only going to get an output when the input is not activated. So what this means this time is we need an input that's normally closed or normally activated, and that's what this diagram here represents. It means that A will allow a signal to pass until it is activated. We see that represented on our truth table. We get an output when A is not activated. So as soon as we activate A, we break the connection, the signal can't pass and the lamp would go out. Therefore, activating A prevents the signal, hence we have a NOT function. So what we can do with these logic functions is we can combine them. So what we see on the right hand side is a combination of our NOT function as well as our OR function. And we'll talk about the diagram underneath in a moment. So what we have is we have a NOT function, and then an OR function. So let's take a look at what that means. If we refer to our ladder diagram, we can see that if A is not activated, then our lamp will light. And we can also see if B is not activated, then we're going to get our output, we're going to get the lamp lighting. We can activate A, breaking the signal here, but we'll still get an output. The signal will just travel around this branch. And we can activate B, providing A is not activated, and we'll still get our output. The only time this lamp won't light, or the only time we won't get an output, is if we activate both A and B. And once again, we see this represented on our truth table because we get an output with every situation except when A and B are both activated. Now this diagram underneath here appears very similar to our AND diagram. In fact, it's a combination of an AND and a NOT, and the only difference on the diagram is this circle at the front here. So what we have is we have an AND and a NOT. The specific name for this is actually a NAND function, N-A-N-D. So what it basically tells us is it's the opposite of an AND function. And again, we can see that's true from our truth table, because if you recall, for an AND function to give an output, A and B had to both be activated. Here we see the exact opposite, because when A and B are both activated, we don't have an output. So the direct opposite of the AND function is the NAND function. Let's take a look at another one of these combined functions, except this time, instead of combining NOTs and ORs to get a NAND, we're going to combine NOTs and ANDs to get a NOR. Now, if you recall, the OR function gave outputs when either A or B were activated, as well as when A and B were activated. And what we can see is the function we're looking at here is the exact opposite. Here, we don't get an output when B is activated on its own, we don't get an output when A is activated on its own, and we don't get an output when A and B are activated. So it's the exact opposite of our OR function. Therefore, this circle here means not OR or NOR function. But let's relate that to the ladder diagram. Here we can see a signal will flow providing A and B are not activated. If we activate A, then the output disappears, the lamp goes off. If we activate B, the output disappears and the lamp goes off, because activating either one of these will open the switch. They're both normally closed. And obviously activating both will also cause the lamp to go off. So the only situation from our truth table that gives an output is when A and B are not activated. We'll take a look at one final example. And once again, the function we're looking at is an OR function. But what this line at the back of the OR function tells us is that it's exclusively OR. If you recall before, the OR function we looked at was almost like an AND OR function, because when A and B were activated, it gave an output. This is exclusively OR. So if we look at our truth table, exclusively OR means it will only give an output signal if A on its own is activated or B on its own is activated. Unlike with the standard OR gate, activating A and B together does not give an output. So the way that that's achieved on our ladder diagram is using combinations of A's and B's on each of these rails of the ladder. Now what we have is we have two A's, one of the A's is normally open and one of the A's is normally closed. And the same with the B's, we have a B that's normally closed and a B that's normally open. If we were to activate B on its own on this top rail, we would get a signal. If we were to activate A on its own on the bottom rail, we would get a signal. Now the purpose of showing you these logic diagrams is so that you can begin to understand some of the combinations of inputs that will produce an output. And there'll be lots and lots of different combinations to produce desired outputs. The other thing that's worth mentioning with these ladder diagrams or these ladder logic programs is we can add additional rungs. So we could have a prerequisite where this program here or this section of the program will only run when the program from the line above runs. So these programs can become very complex, but they use these basic logic functions. Okay, so now we have a basic understanding, first of all, of what a PLC is and some of the functions and operations the PLC can perform. All of this is based on receiving inputs and controlling outputs. So now we're going to look at a specific system in a wind turbine, and we're going to look at the wind turbine pitch system and some of its requirements. So the first thing to understand is the purpose of the wind turbine pitch system. So what we have on the screen here is a wind turbine power output curve. Now ideally, we want to be producing rated power, but what we can see from this diagram is that we can only achieve rated power between wind speeds of 14 meters per second and 25 meters per second. This will vary from turbine to turbine, but in the case of this diagram, peak power or rated power is achieved when winds are at speeds between 14 meters per second and 25 meters per second. At wind speeds below 3.5 meters per second, the wind turbine doesn't engage, meaning the blades will be feathered. They won't be catching any of the wind. But when the wind speeds exceed 3.5 meters per second, we can pitch the blades into the wind and begin catching wind because we're now able to produce some power. At low wind speeds, the amount of power we produce is relatively low, and at higher wind speeds, the amount of power we can produce increases. But the important thing here is what happens at wind speeds of 14 meters per second. What we don't see is the wind turbine producing more and more and more power the higher the wind speeds. Instead, what we see is the power output levels. So what's happening here is the pitch system is adjusting to allow some of the energy in that wind to pass. We're only catching the optimum amount to continue producing rated power. And also, when we get to 25 meter per second winds, we need to stop the turbine. So again, we need a function that's going to take the blades out of the wind entirely. So for the next diagram, we're interested in the section between when we start generating to when we reach rated power or maximum power output. Now this diagram here introduces the concept of synchronous speed. So at the centre of the diagram here, we have the synchronous speed. Our x-axis is the rotor speed, and the y-axis is the torque produced when we're motoring, or the torque absorbed when we're generating. Now it's important to point out that torque is directly related to power. So the higher the torque, the higher the power consumed when motoring, and the higher the torque absorbed when generating, the more power we produce. So this synchronous speed here can be calculated using the formula at the bottom, 120 times the frequency divided by the number of poles. Now just for information, if we had a 4-pole generator connected to the grid at 50 Hz, then this synchronous speed would be 1500 RPM. So I want you to imagine for the moment that this speed here is 1500 RPM. Now at 1500 RPM, the machine is neither motoring because the speed's too high to motor, and it's also not generating because the speed's too low to generate. In effect, it's idling along and it's neither producing nor consuming electricity. In reality, that wouldn't be the case because of friction and so on, but let's assume that we're idling along at 1500 RPM and we're neither producing nor absorbing electricity. So here comes the interesting part, because if we have the rotor within our electrical machine, and we've just said that it's idling along at 1500 RPM, then when we place a load on that machine, meaning we apply a torque in the opposite direction, then as you can imagine, the machine's going to slow down. So anytime we apply a torque to an electrical machine, which causes it to slow down, we're going to move from left to right on our diagram. And the reason we're going to move from left to right is because we're slowing that machine down. The speed might drop to 1400 RPM as an example, which means we're now motoring. But what we notice is that there's a maximum torque that this machine can supply. And in this case, it does occur at around 1450 RPM. So at 1450 RPM, this machine is going to be producing its maximum torque. If we continue to increase the torque, so referring to our diagram on the left-hand side, then in actual fact what happens is the machine can no longer produce the same levels of torque. So the more we slow that machine down, the less torque we're able to produce. But here's the important thing in relation to our generator. So once again, if the machine is happily idling along at 1500 RPM and we apply an additional torque in the same direction as the speed, then what we're basically doing is we're trying to speed that machine up. The torque that we apply is going to make it rotate faster than 1500 RPM. So this time we're moving left to right in relation to our synchronous speed. Now let's say, for example, we're able to apply enough torque to rotate that machine at 1600 RPM. Well, at 1600 RPM, we're going to be generating because the torque that we're applying is speeding the machine up. But if we continue to increase the speed to 2000 RPM or 3000 RPM, then what we can see is that the torque reduces. And if the torque reduces, the amount of power output also reduces. Where we're getting to is that there's an optimum speed that we want to spin that generator at. So if the synchronous speed is 1500 RPM, let's assume for the purpose of this video that we want to spin the generator at exactly 1550 RPM in order to generate rated power. Okay, so now we understand what the desired output is for our wind turbine pitch system, we can begin to look at how a PLC might help us achieve that. Okay, so here we have the drivetrain for a wind turbine, and you'll recognise the majority of these components. We have the hub on the left-hand side connected to the main shaft. We have the main shaft providing an input to our gearbox, and the output to the gearbox is the high-speed shaft, which turns the rotor within our generator. Now what we've just said is that we want that generator to rotate at 1550 RPM. So we need to consider our inputs for our PLC program. Although we said our desired output was a generator rotational speed of 1550 RPM, in terms of our PLC system, that's going to need to be an input. Within the generator here, we have a device called an encoder, and all an encoder does is measure rotational speed. So our input for our system is an encoder that measures the rotational speed of our generator. On its own, it can't do anything with that information. It might measure the speed and find that it's exactly 1550 RPM, which is perfect. But it may measure that speed and find it's 1600 RPM or more, in which case we're not generating our optimal power. So how does that generator encoder achieve the output? Well, the output in this case is going to be our pitch motors. So each of our wind turbine blades, which will be connected to the hub here, would have their own pitch motors. And what the pitch motor does is control the pitch of the blade. So let's have a sketch for the cross section of our blade. And if our generator encoder is measuring a rotational speed of 1550 RPM, then we know that we're achieving just the right amount of lift in order to produce that rotational speed. However, if that generator encoder measures a speed higher than 1550 RPM, then we're going to need to pitch the blade out of the wind or feather the blade. So we would need to change the pitch angle of our blade, like so. We're pitching the blade out of the wind to achieve less lift. Now the consequence of that may be that the generator begins to slow down, and if the generator encoder measures a decrease in speed, such that we drop below the set point, then the blade is going to need to re-pitch back into the wind. So what we have, if you like, is a kind of balancing act. The generator encoder measures the rotational speed. At 1550 RPM, there's no need to make an adjustment. If the speed increases past a given set point, let's say for example that's 1575 RPM, then the PLC is going to need to send a signal to the output to reduce the pitch of the blade. Reducing the pitch of the blade may cause the speed of the generator to decrease, and let's say it drops below a set point of 1525 RPM. It would then pitch the blades in the opposite direction in order to catch more of the wind. So we have our input, the generator encoder. We have the PLC program that receives that information and controls the output, and the output in this case is the pitch motors. Now one other thing that's worth mentioning is we may have additional inputs, and I've mentioned there the anemometer. Now the role of the anemometer is to measure wind speed, and what we said was if the wind speed was below 3.5 meters per second, then we would need to pitch our blades out of the wind. And if the wind speeds were above 25 meters per second, we would also need to pitch the blades out of the wind or feather the blades. So if you like, the role of the anemometer should sit above our original input, because the generator encoder only comes into play when we're in generating mode. The input from the anemometer will communicate with the PLC in order to pitch the blades out of the wind when necessary. If we were to visualize this on a ladder diagram, then the relationship between the generator encoder and the pitch motors would sit on a separate line to the relationship between the anemometer and the pitch motors. And the encoder line of the program would only be executed providing the anemometer element of the program signaled that it was appropriate to do so. So to summarise, in this video we've looked at a general overview of PLCs And we've also looked at some basic logic functions. We've spoken about the requirements of a wind turbine's pitch system, and then we've looked at how these requirements can be achieved using PLCs and PLC functions.